Okay, guys, welcome to my video. Today we'll be going over finding the pH or pOH or hydronium ion concentration or hydroxide ion concentration of strong acids and bases. So why do I specify strong acids and bases? Because they're different in terms of reactivity of weak acids and bases. And the reason is because strong acids and bases dissociate completely, right? So 100% of your concentration that you start with is going to be 100% of the concentration that you end with. And weak acids and bases don't do that. They only dissociate partially. So let's look at this first problem. And it's find the hydronium ion concentration, hydroxide ion concentration, pH and pOH of a 0.365 molarity calcium hydroxide solution, right? So you can see that a little on the side, I have um, key equations. So these are going to help us find out or help us solve the problem, right? So what is hydronium ion concentration? And this is H3O plus. So it's going to be H3. Oh, that does not look nice. Okay. So this is H3O plus. Hydroxide, of course, is OH minus. You guys should know that from your General Chemistry 1 polyatomics. Okay, so first of all, this is a base. Calcium hydroxide is a strong base. What is it specifically, though? It's CaOH2, right? So let's draw exactly the equation that we have here. And how it disassociates is into calcium ion and hydroxide ion. So Ca2 plus OH minus, but don't forget we have two OHs. So we have to balance the equation. And this is actually important because we have to set up a molar equation because, we have 0.365 molarity of calcium hydroxide, but we have, when that splits up, for every one calcium hydroxide, two hydroxide ions. So how are we going to set that up? 0.365 calcium hydroxide times 2 moles of OH minus for every 1 mole of CaOH2. Okay, so that would mean that our hydroxide ion concentration is going to be um so OH concentration equals 0.730. We're going to keep that to 3 sig figs in molarity. We already have one of the four parts of our problem. So now we're going to move on to finding the hydronium ion concentration. So if you look to our key equations on the side, we can see that Kw expression, and Kw is basically in pure water, a very, very small amount of it disassociates into hydronium ion and hydroxide ions. And that small amount is 1.00 times 10 to the negative 14. But we can actually use this for strong acids and strong bases. And we're going to use that to find the hydronium ion concentration. So how are we going to do that? Well, Kw equals, actually, let's not do that. So we're going to say that, rearranging the equation, H3O plus equals 1.00 times 10 to the negative 14 over the concentration of OH, which we have, right? So that's gonna be so that equals 1.00 times 10 to the negative 14 over, I'm just writing in our specific amount, 0.730 molarity. These are both concentrations. Well, technically it's concentration squared. Um, okay. So our answer for that, our hydronium ion concentration is, once we do the math, it's going to be 1.37 times 10 to the negative 14. And so what we're going to do is now we're going to plug these into our other equations, right? So, oops. Um, so we can start with either one. It doesn't matter because we both have those two pieces. We can do pH first because everyone loves pH. So that's going to be pH equals negative log of 1.37 times 10 to the negative 14. I apologize for my handwriting. And that's going to equal 13.863. And there is a specific pH rule in terms of sig figs. So whenever you log something, the log rule, so we had three significant figures, right? That's what we started with in the problem. That's what we're trying to maintain, which means that three significant figures is going to be maintained after the decimal point. So these three are the significant figures. This 13 we don't really care about. It's all about past the decimal point. Oops. Um, okay. So now for pOH. Now there's another way we can do this. There's an equation that I will show you guys in a second. But we have the hydronium ion concentration, so we might as well use that one because it's easily accessible. But there's a less mathy way of doing this. Okay, so this is going to be the negative log of 7.730. This is all molarity, but we don't need to write in the units since it's not our final answer. And that is going to equal 0.137. And pH has no units, right? Well, there's another way of doing this as well, in fact. So there's another equation, and that's that 14 equals pH plus pOH, which means that once we find one, pH or pOH, we can find the other. So in this case, we found pH first, right? So we said that that is 13.863 plus pOH. Um, and what we're gonna find, what we're gonna do is minus that isolate pOH minus 13.863. Have another problem for you guys to do on your own, but we'll get to that in a second. We're going to do that on both sides. Minus 13.863. And what you'll find is that the pOH is once again 0.137. Okay? So what we're gonna do is well, we're done. These are our four answers here. So we got that, um, that boxer answers, these, right? That's supposed to be in molarity. pH has no unit. But I have a problem for you guys. Here it is. So, it's going to be similar to the one we just did. And here are the answers, right? And I'm going to give you a hint. If you don't want it, you can pause here. The hint is sulfuric acid is H2SO4. So you have to multiply 0.250 by 2. So your concentration of hydronium ion is 0.500. All right. And thank you for tuning in. I hope this helped explain some things. If you have any questions, you can comment them and I'll try to get back to you as soon as possible. Um, and if you like this video and would like to see more, please subscribe. I plan to post regularly and I take recommendations for what you guys want to see in terms of content. If this helped as well, please make sure to drop a like as it really helps get my content out there to help a large audience. And yeah, thanks guys.